Welcome back to the channel. Today we're switching gears to Python for forensic chemists. I'm incredibly excited. The series is exciting. I actually had a hard time figuring out how to get started. I still might make a few pivots, but suffice it to say that there's a lot that we can do based on what we've accomplished in our Python for Chemists series that we just completed. Here you can see we have introduced this idea. We've shown how you can use pub chem pi to get cast numbers, smile strings, compare chemical structures. So we were evaluating a bunch of different sugars, lots of stuff in here, and we concluded with Lipinski's rule of 5. And so we could take many of these same approaches and apply them to our forensic chemistry series, but we're going to take a slightly different angle and focus on a lot of other aspects as it relates to how we can use Python to solve these types of problems. So let me switch gears a little bit. So if we go to the data in brief, this is where the data was sourced. And this article is by Arjen van Asten. I think I've met him at a mass spec conference, but these guys are really smart. They're all various forensic experts in the Dutch National Police, Dutch Customs Laboratory, all these wonderful folks in the Netherlands. And so great guys to follow. They have many publications in this space if you want to understand not just spectroscopy, but also some spectrometric approaches as well. And so they have a data set of near-infrared spectral data of illicit drugs and forensic casework samples analyzed by 5 portable mass spectrometers operating in different wavelength ranges. And so this would be a multi-video series. In this video, we're just going to talk about the general aspects of the data, the publications, some highlights that we're going to tackle in the future videos. And then once you're oriented, we'll go back and start writing some code with that familiarity. So be sure to subscribe to the channel if you want to be notified when we continue on this journey. And so there is a full-length article that you can access here where it talks about the importance of wavelength selection. We'll go there in a little bit, but let's first review what's known in this data in brief article. This is an open source article, so is their data, and so is most of the data on this channel. So if you want some unique data sets that's published, that's different than what you might see on other data sources, this is a great way to go. And so here they talk about the importance of basically ways to detect controlled substances, particularly as more designer drugs come on the market, and a way to do this quickly and on site. And so you don't want to have to make all your measurements at the lab, but ideally you could have some sort of presumptive measurement, some idea of what you've got determined from a field test. As most folks in my field would say, colorimetric tests are great, they're fast, they're cheap. However, they're prone to mistakes, false positives. As formulations of drugs change, these tests might not be updated quickly enough. And so you need something that's more robust, and near-infrared spectroscopy is one of those approaches because it is non-destructive and has many other benefits, as well as being portable. Next, they tell us that the NIR spectrum is from 780 to 2500 nanometers. And so this gives you some idea of the types of modes you're going to be measuring. And so at this point, the molecules are still absorbing this energy, but we're going to be looking at vibrations, some of the weaker signals, not quite in the visible spectrum. Over the course of the study, they have 430 samples, including regularly encountered illicit drugs, adulterants, bulking agents. So you can see there's a lot of information here, a lot we can do with this data set. They're also going to be evaluating several different portable near-infrared spectroscopy instruments and comparing that to a benchtop standard instrument. So a really good study for us to evaluate for ourselves, which might be the best based on its ability to detect these various drugs, their adulterants or bulking agents as well. And there's usually a trade-off when it comes to benchtop instruments and portable instruments. And one obvious way is with the wavelength range of the instrument. So instead of covering the full bandwidth of the near-infrared range, you're looking at some smaller portion of that, and thus you might have some trade-offs when it comes to what you're able to detect and what's being left behind as far as undetected because of the optics. So we'll take a look at that as well. The data is in the form of a table. We have the raw unprocessed data in an Excel format, and then the replicated averaged data, which we might just start with that. The data was all collected from the Dutch National Police and the Greater Amsterdam area. So again, these are just really relevant samples. and the data can be accessed using these links here. And so check that out. You can also let them know on LinkedIn that we are talking about their data. This is really exciting. So they actually did a full comparison study here where they look at the importance of wavelength selection and on-scene identification of drugs of abuse with portable near-infrared spectroscopy. So it's great they did their study and also have a way for us to look at the data and run our own studies and explore it for learning purposes. They talk a little bit more about the wavelength ranges. So the whole point of their study was to evaluate of these portable near-infrared sensors and how they compare to the full bandwidth of a benchtop FTIR system. If we scroll to tab 1 in their main article, we can see we have the benchtop instrument. This covers almost to the UV to the full IR range. So let's start digging in and we can begin evaluating this set a little bit more. In our notebook, I have covered the abstract a little bit. I talked about some of the considerations we're going to be making in this data set. So in lab versus in situ analysis, the robustness of the measurement. We'll also talk about classification. What drug do we have? What has it been adulterated with? And then the quantitative aspects as well. How much is there? How much cocaine are we talking about? When it comes to the near infrared spectrum, it lies just to the right of the visible spectrum. So as the wavelengths get larger, so in the visible spectrum, we're here. It's a very narrow range of the full electromagnetic spectrum. And as we move into the infrared here, we start talking about that heat. We are just beyond the visible range on the red side. So infrared, red side, ultraviolet on the blue-violet side of the visible spectrum. And so based on this, we can infer the types of energy we're talking about. So now we're talking vibrational, rotational type energies, and what we're able to then monitor as it relates to the patterns available to us when we look at these drug tablets, these powders, these excipients, and adulterants. And so as it relates to that, there's a lot of things we're going to do. The first video, we're actually going to tackle looking at how we control some of this data. So in the context of forensic analysis, we need to be sure that we're using quality data. And when it comes to near-infrared spectroscopy, we have a lot of effects of light scattering on the vial, on the excipients, on just things that aren't necessarily related to the material. And so one way to control that data is to use the standard normal variate, or is to compute the standard normal variate for each of these samples. And that helps in correcting the scatter for these. Let me zoom in a little bit more. And so that helps in correcting the scatter effects of the spectral data. And so I won't go into how we do that in this video. This is where we'll start in video 2 of this series. Now that we've introduced the problem, we're somewhat familiar with the type of data we're going to get and where this exists in the electromagnetic spectrum. If you want to be notified when this next video drops, be sure to subscribe to the channel. And in the next video, we'll be tackling the standard normal variate and how we can use that to pre-process our data before we do anything else with it. In any case, I'll see you in the next video. Peace.